Hello there, and welcome to the Deep Somna. Welcome. You've found your way here, and that's enough. Whatever the day held, the noise of it, the pace of it, the things left unfinished, you can let all of that soften now. There is nowhere else you need to be. Nothing you need to solve or carry into this moment. Just the quiet weight of your body settling, the gradual slowing of your breath, and the gentle invitation to look, if only in your mind, toward the sky above you. Even now, with walls and ceilings and clouds between you and the stars, they are there. The same stars that have burned for millions and billions of years. The same darkness that has held galaxies, swallowed light, and stretched in every direction since long before the Earth existed. It is all still there, patient, indifferent to the hour, untroubled by anything that happened today. Tonight, we are going to travel through that sky together. Not quickly, not urgently. We will move the way starlight moves, steadily, without hurry, covering distances so enormous that the numbers lose their edges and become something closer to a feeling, a sense of depth, a sense of wonder that doesn't demand anything from you, doesn't require you to remember the details or hold on tightly to the facts. You can let the details blur. The science here is real, and we will touch it gently, honestly. But the goal tonight is not to learn. It is to rest inside the feeling of how large and old and extraordinary the universe is, and to let that vastness quietly carry you towards sleep. So settle in. Let your shoulders drop a little. Let your jaw unclench. Breathe in, and then out slowly. The cosmos is ready when you are. Astronomy is, at its heart, the study of everything above us. Every point of light in the night sky. Every planet, every moon, every star, every galaxy. Every dark region between the galaxies where almost nothing exists. And yet even that nothing is not quite empty. Astronomy is the science of distance so profound that we measure them not in kilometers but in the time it takes light to travel. And light, moving at 300,000 kilometers every second, is the fastest thing we know. When you look at the moon on a clear night, the light reaching your eyes left the lunar surface about 1¼ seconds ago. A small delay. Almost nothing. But the sun, our own sun, sends us light that is 8 minutes old by the time it warms your face. The nearest star beyond our sun, a faint companion called Proxima Centauri, is over 4 light years away. That means the light from it entering your eyes tonight began its journey more than 4 years ago, traveling without pause through the cold silence of space, just to meet you here. And that is just the nearest star. The Milky Way. Our galaxy. The great river of stars you can sometimes see arsing across the sky on a clear dark night, is roughly 100,000 light years across. Light leaving one side would take 100,000 years to reach the other. Inside this galaxy are somewhere between 200 and 400 billion stars, each one a sun, many of them likely surrounded by worlds of their own. And the Milky Way is only one galaxy among many. In the 1920s, the astronomer Edwin Hubble made one of the most significant discoveries in the history of human thought. Those faint smudges of light that earlier astronomers had called nebulae, small cloudy patches in the sky, were not nearby clouds of gas. They were entire galaxies, vast as large or larger than our own Milky Way, lying at distances so great the mind struggles to hold them. Since Hubble's time, telescopes have grown in power and sensitivity until we now estimate there are roughly 2 trillion galaxies in the observable universe. 2 trillion, each containing hundreds of billions of stars, each of those stars possibly hosting planets. The scale of it is not frightening. It is simply so large that it becomes, in a quiet relief. The universe is so immense that every worry, every tension, every weight you carried into bed tonight is held within something so much larger than itself that it naturally loosens its grip. Let that thought stay with you for a moment. You are one small, warm, living thing on one small planet, circling one ordinary star, at the edge of one galaxy, among 2 trillion others. And somehow, impossibly, you are aware of all of it. That awareness is not nothing. It might, in fact, be one of the most extraordinary things in the known universe. But we are getting ahead of ourselves. Let us begin more slowly, closer to home. Imagine you are floating just above the Earth's atmosphere, high enough to look down at the curve of the planet, the blue-white glow of it against the black. Below you, the oceans, the thin skin of air, the land where everything you have ever known is taking place, and above you, nothing but open space in every direction. Stars scattered across the dark like grains of salt on black cloth. From here, you could look inward toward the sun, which even from this distance is blazing and overwhelming. The sun is, by any human standard, enormous. Its diameter is about 109 times that of Earth. You could fit over 1 million Earths inside it. It contains more than 99% of the total mass of our entire solar system. All the planets, all the moons, all the asteroids and comets and drifting dust, everything, together make up less than 1% of the solar system's mass. The sun does not merely sit at the center of our solar system. In a very real gravitational sense, it is our solar system. The planets are crumbs around a blazing bulk, and yet that blazing bulk is itself just one ordinary star among hundreds of billions in the Milky Way, positioned roughly 2/3 of the way from the center, on one of the galaxy's quiet spiral arms. The sun is powered by nuclear fusion. Deep in its core, where temperatures reach about 15 million degrees Celsius, and pressures are unimaginable, hydrogen atoms are fused together to create helium. In that process, a tiny fraction of mass is converted into energy that travels outward through the dense solar interior, a journey that can take hundreds of thousands of years just to escape from the core to the surface. Then from the surface, the energy races across space as light and heat and reaches Earth in about 8 minutes. That light has been sustaining life on this planet for nearly 4.5 billion years. It drives the weather, the seasons, the growth of every plant, the warmth in your skin on a sunny afternoon. All of it, the product of hydrogen, fusing into helium 93 million miles away. The sun is about 4.5 billion years old, roughly middle-aged for a star of its type. It has enough hydrogen fuel remaining to keep burning for approximately another 5 billion years. In the deep future, long after anything we could call civilization has risen and faded, the sun will exhaust its core hydrogen and begin to change. It will expand outward, growing into what astronomers call a red giant, swelling to perhaps 100 100 times its current size. By the time it reaches that phase, it may engulf the inner planets. The Earth may or may not survive intact. Scientists are not entirely certain, but that moment is so far away it belongs more to imagination than to any practical concern. For now, the sun shines steadily, as it has for billions of years, as it will for billions more. Let your breath slow a little. There is no hurry here. From your imaginary vantage above the Earth, let your gaze drift outward, past the glowing disk of the sun, out into the solar system. The 4 inner planets, Mercury, Venus, Earth, and Mars, are small, rocky worlds, orbiting close to the sun's warmth. Beyond them, a belt of asteroids. And then the gas giants begin. Jupiter, the largest planet in the solar system, is a world of storms and immense gravity. Its famous Great Red Spot is a storm that has been churning for centuries, larger in area than Earth itself. Jupiter's mass is more than twice that of all the other planets combined, and its gravity, that immense gravitational presence, plays a quiet but important role in the story of Earth's survival. As asteroids and comets drift through the solar system, Jupiter's gravity frequently pulls them off course, flinging them away or drawing them in toward itself. Scientists believe this has shielded the inner solar system, including Earth, from many potential catastrophic impacts over billions of years. In 1994, astronomers watched as the comet Shoemaker-Levy 9, torn apart by Jupiter's tidal forces into a string of fragments, slammed into Jupiter's atmosphere over several days, leaving dark scars the size of Earth visible for months. Jupiter absorbed that collision so we did not have to. Beyond Jupiter lies Saturn, encircled by its famous rings. Those rings, which look so permanent and ancient in every image we have ever taken of them, are actually surprisingly young, perhaps only about 100 million years old. That means they formed long after the dinosaurs walked the Earth. They are made mostly of water ice, ranging from tiny grains to chunks the size of houses, and slowly, steadily, they are losing material, with ice particles spiraling down into Saturn's atmosphere in what scientists call ring rain. If this continues, the rings may largely disappear within another 100 million years or so. Something that looks eternal is not. That thought is not sad. It is simply honest, and there is something restful about it. Even the most beautiful structures in the cosmos are temporary. They rise, they exist for a time, they change or fade. And the universe continues, patient and vast. Beyond Saturn, Uranus and Neptune spin in the cold outer dark. And beyond them, the Kuiper Belt, a broad ring of icy bodies stretching into the deep solar system. And then, even further out, the Oort cloud, a vast and distant sphere of comets, extending perhaps a quarter of the way to the nearest star. When a comet falls inward toward the sun, it may have begun its journey from that remote shell, dislodged by some gravitational nudge after orbiting quietly out there for billions of years. Our solar system is large, far larger than it might seem from our cozy position on Earth. And yet within the Milky Way it is nearly invisible. A pale dot orbiting a pale star in a quiet corner of the galaxy. Let that settle over you like a blanket. The smallness is not a diminishment. It is a kind of freedom. Your worries are real, but they exist inside something immeasurably large. When the universe is this size, there is room for everything, including rest. Now, as we move outward from our solar system into the wider galaxy, the character of space begins to change. The nearest stars to our Sun are the three-star system of Alpha Centauri, about 4¼ light years away. Even traveling at the fastest speeds any human spacecraft has ever achieved, reaching those stars would take tens of thousands of years. The distances between stars are, by any human measure, incomprehensible, and yet those distances are not entirely empty. Between the stars, space is threaded with thin clouds of gas and dust. Hydrogen, mostly, along with helium, trace amounts of heavier elements, and complex organic molecules. These interstellar clouds are the raw material from which new stars and planets are born. When gravity causes a region of such a cloud to begin collapsing inward, the material compresses and heats. Over hundreds of thousands of years, a protostar forms. Then, if the mass is sufficient, nuclear fusion ignites in the core, and a new sun begins to shine. We can see this process happening in places like the Orion Nebula, a stellar nursery about 1,400 light years away, where new stars are still being born today. In images from telescopes, it appears as a glowing cloud of pink and orange light, lit from within by the hot young stars newly formed inside it. It is a place of creation on a cosmic scale, beautiful and slow, unfolding over millions of years. The stars born in such clouds are not all alike. They vary enormously in mass, temperature, color, and lifespan. The most massive stars burn brilliantly but briefly, consuming their fuel in only a few million years before dying in spectacular explosions. Smaller stars, like our Sun, burn more steadily for billions of years. The smallest stars, called red dwarfs, burn so slowly and dimly that they may shine for trillions of years, far outlasting any star we can see with the naked eye. When a massive star ends its life, it does not simply go dark. It explodes in a supernova, one of the most energetic events in the known universe. In the moments of that explosion, temperatures and pressures reach extremes that forge heavy elements: gold, platinum, uranium, elements heavier than iron, which cannot be made in the steady burning of a star's core, are created in the final violence of a supernova and scattered outward into space. They drift through the galaxy for millions of years, mixing with other material, eventually gathering into new clouds, new stars, new planets. The gold in any piece of jewelry you own was created in the death of a star. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it came from stars that lived and died long before our sun existed. You are, in the most literal sense, made of stardust, not as a metaphor, as a fact of chemistry and astrophysics. When you look up at the night sky, you are not looking at something foreign or distant from yourself. You are looking at your own origins. The atoms that compose your body have been part of nebulae, of stars, of supernovae, of the slow, cold drift of interstellar space, and eventually of you. The universe made you out of itself, and now, through your eyes, it looks back at its own creation with something like wonder. Take a slow breath. Let that thought move through you gently, without forcing it into any particular meaning. Just let it rest there. You don't need to remember the details. You don't need to hold on to the numbers or the names. Just the feeling is enough. the feeling of being part of something very, very old and very, very large. And as you breathe, let your body grow a little heavier. Let the tension in your muscles soften. The stars are still there above you, steady and quiet, burning their ancient light. The galaxy is turning, as it always does, slowly and without any urgency. The universe is expanding in every direction, a little faster each moment, carrying everything gently outward into the deep. There is nowhere you need to go tonight. Nothing you need to become or solve or understand. The cosmos holds you just as it holds everything else, without judgment, without condition, in the same patient dark that has always been there everywhere. For as long as there has been a universe at all, we have been drifting together through the solar system, past the gas giants, and out toward the stars. Now let us go further. Let us leave the familiar neighborhood of our sun behind entirely and begin to think about what lies beyond, in the deep structure of the galaxy, and beyond the galaxy, into the vast architecture of the universe itself. But as we travel further, let your body remain exactly where it is. Comfortable, still, growing heavier with each breath. The journey tonight is entirely in the imagination, which makes it the safest and most restful kind. One of the most remarkable things about looking at the night sky, something astronomers sometimes call the deepest truth of observational astronomy, is that you are never seeing the universe as it is right now. You are always seeing it as it was. The light entering your eyes left its source some time ago. For nearby stars, that time might be decades or centuries. For distant galaxies, it might be billions of years. The farther you look, the further back in time you see. This is because light, for all its speed, is not instantaneous. It travels at roughly 300,000 kilometers per second, which is incomprehensibly fast by any human standard. But the universe is so large that even at that speed, light takes time. Real, measurable time. The light from the Andromeda galaxy, our nearest large galactic neighbor, left it about 2.5 million years ago. It was traveling through space while our distant ancestors were still learning to make stone tools. And it has only just arrived here, now, in time for you to see it as a faint smudge in the constellation of Andromeda on a dark autumn night. Telescopes, then, are not just tools for seeing far, they are tools for seeing back. When astronomers point the Hubble Space Telescope or the James Webb Space Telescope at a faint, distant object and gather its light, they are receiving information from the early universe. Images of galaxies as they were 1 billion, 10 billion years ago. Some of the most distant objects ever observed sent their light toward us when the universe was less than 1 billion years old. When our sun did not yet exist, when the earth had not yet formed. This means that right now, tonight, as you lie quietly in the dark, light from the very beginning of the universe is still traveling through space. Ancient photons born in the fires of the Big Bang, still moving after nearly 14 billion years. They have not been absorbed, they have simply kept going. Their wavelengths stretched by the expansion of the universe from visible light into microwaves, too long for our eyes to detect. But radio telescopes can hear them, and that faint background hum, the cosmic microwave background, is one of the most important things ever discovered. It was found almost by accident in 1965. Two radio astronomers named Arno Penzias and Robert Wilson were working with a large antenna in New Jersey. They kept detecting a faint, persistent noise in their equipment that they could not explain. They checked everything. They even removed pigeons that had nested in the antenna and cleaned out what they delicately described as a white dielectric material. The noise persisted. It was coming from everywhere in the sky simultaneously. They had detected the afterglow of creation. That faint microwave hiss, uniform in all directions, is the stretched remnant of the light that filled the universe when it was only 380,000 years old. At that moment, the cosmos had cooled enough for electrons and protons to combine into the first hydrogen atoms. Before that moment, the universe was so hot and dense that light could not travel freely. It was constantly scattered, trapped in a kind of fog. When the fog cleared, light poured outward in all directions. That light is still traveling today. We call it the cosmic microwave background, and it is the oldest light we can observe. Its temperature today is about 2.7 Kelvin, just barely above absolute zero. The universe, in its vast cold age, has cooled dramatically from the fierce heat of its birth. But those first photons are still there, still filling every corner of space, carrying within them a map of the infant universe's structure. The tiny fluctuations in that map, temperature differences of only a few millionths of a degree, represent regions where matter was very slightly denser. Those regions, over hundreds of millions of years, attracted more material, grew under their own gravity, and eventually became the seeds of the galaxies, galaxy clusters, and cosmic filaments we see today. The universe's large-scale structure, everything we observe, grew from those almost imperceptible ripples in the early cosmos. The whole story of stars and galaxies and planets, and you is, in some sense, written in that faint ancient glow. You can let that thought drift. You don't need to hold it tightly. Just let it float past. Now, one of the things that makes astronomy so quietly astonishing is not only what we can see and measure, but what we know must exist even though we cannot see it at all. This brings us to one of the deepest mysteries in modern science: dark matter. When astronomers study galaxies, they can observe how fast the stars within them are moving, how quickly they orbit the galaxy's center, and when they calculate those velocities against the amount of visible matter in the galaxy, something doesn't add up. The stars in the outer parts of galaxies are moving much too fast. According to the laws of gravity, they should be moving more slowly, just as the outer planets of our solar system move more slowly than the inner ones. But they don't. They move at speeds that suggest there is far more mass in those galaxies than we can see. This observation was made carefully and rigorously by astronomer Vera Rubin in the 1970s, building on earlier work. Her measurements of galaxy rotation curves, the relationship between a star's distance from the galactic center and its orbital speed, showed that galaxies must contain enormous amounts of invisible mass. Without it, they would fly apart. The visible stars, gas, and dust simply cannot account for the gravity that holds them together. This unseen material was named dark matter. And it is not dark in the way a shadow is dark, simply blocking light. It is dark in the sense that it does not interact with light at all. It neither emits it, reflects it, nor absorbs it. It passes through ordinary matter almost without any interaction whatsoever. It is as if there is a second kind of substance in the universe that fills the same spaces ordinary matter fills, but that we cannot touch, see, or directly detect in any way we currently know. And there is a lot of it. Astronomers estimate that dark matter makes up about 27% of the total mass energy content of the universe. Ordinary matter, all the atoms, all the stars, all the planets, all the gas clouds, everything we have ever seen or touched or measured, makes up only about 5%. 5%. The rest is dark matter, and something even more mysterious that we will come to in a moment. Right now, in the darkness of your room, dark matter is likely passing through you. Physicists believe the galaxy is permeated by it, a halo of dark matter extending far beyond the visible disk of the Milky Way, a vast invisible scaffolding holding the galaxy together. And as the Earth moves through this halo, dark matter particles, whatever they are, may flow through the walls of your house, through the floor, through your body, without interacting in any way we can measure. They carry no charge. They produce no light. They simply pass through, as indifferent to your existence as the galaxy's edge is to the town where you sleep. Scientists around the world are trying to detect dark matter particles directly. Deep underground, in old mines in Canada, in tunnels beneath mountains in Italy, in laboratories beneath the surface in South Dakota, incredibly sensitive detectors wait in cold darkness, shielded from the constant rain of cosmic rays and other radiation that would drown out any signal. These detectors are looking for the rare occasion when a dark matter particle might bump into an ordinary atom, producing a tiny, measurable disturbance. So far, nothing conclusive has been found. But the search continues, patiently, year after year. Every null result tightens the boundaries of what dark matter could be. Every empty detector teaches us something. Science advances not only through positive discoveries, but through the careful elimination of possibilities. We are narrowing the circle around the truth, slowly, steadily. And then there is dark energy. If dark matter is mysterious, dark energy is in some ways even stranger. It is not a particle. It does not seem to be a substance at all in the conventional sense. It may be a property of space itself, and it makes up approximately 68% of the total energy content of the universe. Here is where the story becomes remarkable. In 1998, two independent teams of astronomers were studying a particular type of exploding star, a Type Ia supernova that can be used as a standard candle, a fixed reference point for measuring cosmic distances. By measuring how bright these supernovae appeared and comparing that to how bright they should be, astronomers could calculate their distance and then, combined with how fast they were moving away from us, determine how the universe's expansion had changed over time. They expected to find that expansion was slowing down. The Big Bang had flung matter in all directions, and gravity should have been pulling things back together, gradually decelerating the expansion. Instead, they found something no one had predicted. The expansion was speeding up. Distant galaxies were moving away from us faster than closer ones, not slower. Something was causing space itself to stretch at an accelerating rate. That something was named dark energy. It appears to be an intrinsic energy of empty space, a kind of built-in push that grows as space expands. The more space there is, the more dark energy there is, and the faster the expansion accelerates. The discovery earned a Nobel Prize in Physics in 2011, and it fundamentally changed our picture of the universe. Today, the universe is expanding in every direction, and it is doing so faster and faster. Distant galaxies are already moving away from us so quickly that the light they emit now will never reach us. They have crossed what cosmologists call the cosmic horizon, beyond which they are forever invisible. Over billions of years, as expansion continues, more and more of the universe will slip beyond that horizon. The observable universe will appear to shrink, not because the cosmos is actually smaller, but because so much of it will have moved beyond the reach of light. In the very far future, timescales of trillions of years, this process will leave the Milky Way's descendants alone in an otherwise dark and empty sky, with no other galaxies visible, no light from beyond our local group. It would be, if any awareness existed then, a profoundly lonely sky, but that moment is incomprehensibly distant. Tonight, the sky is full of light, full of galaxies and stars and ancient photons, still crossing the cosmos. Let your breathing slow a little more. There is no urgency. The universe expands at its own pace, and you can rest at yours. We have spoken of dark matter holding galaxies together, and dark energy pulling the universe apart. These two forces, both invisible, both dominant, are in a kind of long, slow tension. Gravity, including the gravity of dark matter, works to draw things together. Dark energy works to drive them apart. So far, on the scale of individual galaxies and galaxy clusters, gravity wins. These structures remain bound. But on the very largest scales, across the expanding fabric of space itself, dark energy is winning. The question of what dark energy truly is remains one of the most profound open questions in all of science. One possibility is that it is simply a cosmological constant, a fixed property of empty space first proposed, somewhat speculatively, by Einstein in his equations of general relativity. He later called it his greatest blunder, when expansion seemed not to need it, but observations of accelerating expansion brought it back. In this model, dark energy does not change over time. Space simply has a constant, inherent energy, and the universe expands at an ever-increasing rate, forever. Another possibility is that dark energy is a dynamic field, something that changes over time, perhaps growing stronger or perhaps weakening. If it weakens, gravity could eventually overcome it, and the expansion could slow, stop, and reverse. If it strengthens without limit, it could eventually overcome not only cosmic expansion, but the forces holding galaxies, stars, planets, and even atoms together, a scenario called the Big Rip. This is speculative, and there is no current observational evidence that it will happen. It is one possibility among several, mentioned here not with any sense of alarm, but simply as a reflection of how genuinely uncertain our picture of the future cosmos remains. We simply do not know. And that honest uncertainty, held gently, is not frightening. It is part of what makes astronomy a living science, rather than a closed book. As you rest, consider that you are lying inside a universe that is simultaneously deeply studied and profoundly mysterious. Scientists have mapped the cosmic microwave background with extraordinary precision. They have measured the expansion rate of the universe, cataloged billions of galaxies, detected gravitational waves from colliding black holes a billion light-years away, and landed instruments on the surfaces of other worlds. And yet the nature of 95% of everything that exists remains genuinely unknown. We are standing on a thin, bright shore at the edge of a very deep ocean. That image is not unsettling. It is simply true. And there is something peaceful about the truth, even when the truth is that there is much we do not yet understand. The universe has been here for nearly 14 billion years. It will be here for an immeasurably longer time still. The questions it poses are patient questions. They will wait. Tonight you don't have to answer any of them. Now let us turn towards something a little more concrete, toward objects of extraordinary density and gravity, toward the places in the universe where the familiar laws of space and time begin to bend and break in ways that are genuinely strange and genuinely wonderful. Let us talk about black holes. A black hole forms when a massive star, one, perhaps 10 or more times the mass of our sun, reaches the end of its life and its core collapses. The core had been supported against gravity by the pressure of nuclear reactions. When those reactions can no longer continue, the support disappears and the core collapses inward. In milliseconds, it goes from a hot, dense ball to something far beyond any ordinary state of matter. If the core is massive enough, the collapse continues without limit, creating a singularity, a point of infinite density, surrounded by a region of space from which nothing, not even light, can escape. The boundary of that region is called the event horizon. Beyond the event horizon, the gravitational pull is so strong that the escape velocity, the speed needed to break free, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. Not particles, not radiation, not information, not anything. From the outside, a black hole is, in a sense, invisible. You cannot see the singularity. You cannot see what is inside. You can only observe the effects, the bending of light from objects behind it, the acceleration of stars orbiting it, the heating of gas falling toward it. And from that evidence, you can infer its existence and even measure its mass. Our own galaxy, the Milky Way, has at its center a supermassive black hole called Sagittarius A. It has a mass of roughly 4 million times the mass of our sun. Yet despite this extraordinary mass, it is currently relatively quiet, consuming little material. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, a glowing ring of hot gas circling the invisible central darkness, photographed using a network of radio telescopes spread across the Earth, working together as a single instrument the size of the planet. There it was, a shadow surrounded by fire, the direct image of something from which no light escapes. Other galaxies host supermassive black holes far more massive, billions of times the mass of the Sun. When these monsters are actively consuming material, the surrounding accretion disk, a swirling ring of superheated gas, can outshine the entire galaxy it sits within. These are quasars, and they are among the most luminous objects in the known universe, blazing with the energy of trillions of suns, visible from billions of light years away. Black holes are not empty. They are not the absence of something. They are a presence, an extreme density of mass warping space and time so severely that our familiar picture of reality no longer applies there. Near a black hole, time itself changes. Einstein's theory of general relativity, one of the most precisely confirmed theories in all of physics, tells us that massive objects curve spacetime. Gravity is not a force pulling objects together in the way Newton described. It is the curvature of spacetime caused by mass. Objects follow paths through curved spacetime, and those paths look like the orbits and trajectories we observe near an extremely massive object, like a black hole. That curvature becomes extreme. One of the most striking consequences is time dilation. The closer you are to a massive object, the more slowly time passes for you compared to someone farther away. This is not a trick of perception. It is not a psychological illusion. Clocks literally tick at different rates depending on the gravitational field they are in. Near the event horizon of a black hole, time would slow to an almost inconceivable degree compared to time far away. If you could hover safely near an event horizon, which you couldn't in practice, but imagine, you would experience time normally. Your heartbeat, your breath, your thoughts would seem ordinary to you. But to an observer watching from a safe distance, you would appear to move more and more slowly, approaching the horizon but never quite reaching it, frozen gradually like an image fading from a screen. Meanwhile, for you, the universe outside would appear to accelerate. Stars living and dying in moments, galaxies evolving in what felt like seconds. This is real. This is physics. And it applies not only to black holes, but everywhere that mass exists. The surface of the Earth is closer to our planet's mass than the atmosphere above, so time passes very slightly more slowly at sea level than at altitude. This difference is measurable. Satellite clocks used in GPS systems tick at a slightly different rate than clocks on the ground, and engineers must correct for this effect to keep navigation accurate. Every time your phone tells you where you are, it is relying on equations that account for the bending of time by gravity. The universe is stranger and more subtle than it looks from the ordinary scale of human experience. But its strangeness, examined calmly, is not threatening. It is wondrous. It reminds you that the world is deeper than it appears, richer in structure and surprise, unfolding according to principles so elegant that even the clocks of artificial satellites must bow to them. Let your mind rest in that strangeness for a moment. Let it be comfortable not knowing all the details. The universe is allowed to be mysterious. And so tonight, are you? We have been traveling a long way together through the dark. Past our sun, past the stars and the spinning galaxies, through the invisible architecture of dark matter and the quiet expansion driven by dark energy, and into the extraordinary gravity of black holes, where time bends and slows. Let us continue drifting, a little more slowly now, deeper into some of the quieter mysteries, the questions that have no complete answers yet, and the experiments and instruments we are building patiently to seek them. Your breathing is slower than it was. Your body is heavier. The thoughts that were sharp at the start of the evening have begun to soften at the edges, the way the horizon softens at dusk. That is exactly where you want to be. Let the words come in gently, like water, without needing to follow every detail. One of the things that astronomy teaches, slowly and steadily over a lifetime of observation, is that the universe contains far more variety than anyone initially suspected. We find objects and phenomena that seem almost impossible, that push the laws of physics to extremes we can barely calculate, let alone imagine visually. Consider neutron stars. When a massive star ends its life in a supernova explosion, the outer layers are blasted into space, and the core collapses. If the mass of that core is not quite enough to form a black hole, it collapses instead into a neutron star. A neutron star is a sphere perhaps 20 kilometers across, roughly the size of a city, containing more mass than the Sun. Its density is so extreme that it is made almost entirely of neutrons, the neutral particles normally found in the nuclei of atoms, squeezed together without gaps. A single teaspoon of neutron star material would weigh billions of tons on Earth. Not billions of grams, billions of tons. The number is so extreme it becomes more of a feeling than a fact. A sense that matter can exist in states utterly beyond ordinary experience. Neutron stars also spin. Conservation of angular momentum, the same principle that makes a figure skater spin faster when drawing their arms inward, causes the collapsing core to rotate faster and faster as it shrinks. Some neutron stars end up spinning hundreds of times per second, so fast that the centrifugal forces would tear apart any ordinary material. Yet the extreme gravity keeps everything bound together. As neutron stars spin, they emit beams of radiation from their magnetic poles. If those beams sweep across the Earth in their rotation, the way a lighthouse beam sweeps past a ship, we detect them as pulses. Regular, rhythmic bursts of radio waves or X-rays, arriving with the precision of the finest atomic clocks. These are pulsars, and they are among the most precisely timed objects in nature. Some pulsars are so regular that they can be used to measure time, as accurately as the best human-made clocks. The first pulsar was discovered in 1967 by the astronomer Jocelyn Bell Burnell, who noticed an unusual repeating signal in her radio telescope data. The signal was so regular and its origin so unclear that her team, briefly, gave it the tentative label LGM-1, Little Green Men, not because they seriously thought it was a message from an alien civilization, but because they could not immediately explain what natural process could produce such a precise, repeating radio pulse. The explanation, of course, turned out to be a rapidly rotating neutron star, which was arguably more remarkable. There is a subset of neutron stars called magnetars, and they are extraordinary in a different way. Their magnetic fields are of a magnitude difficult to describe in ordinary terms. A typical refrigerator magnet measures about 1/100th of a Tesla. Earth's magnetic field at the surface is perhaps 50 microteslas. A magnetar's magnetic field can reach 1,000,000 billion Tesla, roughly 1 trillion times stronger than the surface of any ordinary neutron star. These fields are so strong, they can affect the behavior of atoms at a distance. They can warp electron clouds around atoms, reshaping their chemistry. They release enormous bursts of X-rays and gamma rays in starquakes, sudden readjustments of the crust of the neutron star. A magnetar outburst detected in December 2004 from a magnetar some 50,000 light-years away, well beyond our galaxy, was powerful enough that it briefly affected Earth's upper atmosphere, despite the vast distance. A single convulsion of a dead star, halfway across the galaxy, that still reached us here. Fortunately, the known magnetars are all safely far away, but they remind us that the universe contains phenomena at scales of energy and intensity that dwarfs everything in ordinary human experience. From these extreme stellar remnants, let us drift outward once more to consider the large-scale structure of the universe, the architecture of galaxies, and the web of matter that connects them. If you could see the universe from an enormous distance, with the ability to observe all matter at once across billions of light years, what you would see would not be a uniform fog. The universe is structured. Matter is not spread evenly. Instead, it forms vast filaments, long threads of galaxy clusters connected end to end, surrounding enormous empty voids where almost nothing exists. This pattern is called the cosmic web, and it is the largest structure in the observable universe. The filaments of the cosmic web are made partly of ordinary matter, galaxies, hot gas, the stuff of atoms, but they are also made of dark matter, which provides the gravitational scaffolding along which ordinary matter has gathered over billions of years. In the early universe, tiny density fluctuations, those almost imperceptible ripples in the cosmic microwave background we discussed, grew under gravity into the seeds of the cosmic web. Dark matter clumped first, forming halos. Then ordinary matter fell into those halos, forming galaxies. Over billions of years, galaxies gathered into clusters and superclusters, connected by those long filaments, separated by the vast empty voids. It is an architecture of breathtaking complexity, spontaneously arising from the simple combination of gravity, expansion, and the initial conditions of the Big Bang. Our Milky Way sits within a galaxy cluster called the local group, which in turn sits at the edge of a larger structure called the Virgo supercluster, which is itself part of an even larger supercluster complex astronomers have mapped and named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains hundreds of thousands of galaxies, spans roughly 500 million light years, and has a total mass of about 100 million billion times the mass of our Sun. And Laniakea is just one supercluster among many in the observable universe. The mind, as it reaches toward these scales, eventually finds the numbers meaningless and settles into something simpler, something more like awe, not the loud, startling kind, the quiet kind, the kind that sits in the chest when you look up on a clear night and see the Milky Way stretched overhead, knowing it is not a backdrop, but a living thing you are inside of, knowing it extends in all directions for 100,000 light years, knowing there are 2 trillion more like it scattered through the dark. That quiet awe is not an emotion you need to chase or force. It is already there, waiting, under the surface of ordinary thoughts, and it is compatible with sleep. You can wonder and rest at the same time. The universe does not require you to be awake to exist. Let your thoughts soften a little more. Now, one of the most exciting frontiers in astronomy in recent years has been the direct detection of gravitational waves, ripples in the fabric of spacetime itself. Einstein predicted these waves in 1916 as a consequence of his theory of general relativity. When massive objects accelerate, when 2 black holes spiral together, for instance, or 2 neutron stars collide, they disturb the geometry of spacetime in waves that propagate outward at the speed of light. For most of the 20th century, gravitational waves were a theoretical prediction. No one had ever detected one. The waves produced by even the most violent cosmic events are extraordinarily faint by the time they reach Earth, because the distances are so vast. The distortion they cause in spacetime is measured in fractions of the width of a proton. Detecting such a subtle change seemed almost impossible. Almost. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a gravitational wave signal for the first time. The instrument consists of two L-shaped detectors, one in Louisiana and one in Washington state, each with arms 4 kilometers long. Laser beams bounce back and forth inside these arms, and the system measures the length of those arms to extraordinary precision. When a gravitational wave passes through, it stretches one arm and squeezes the other, alternating back and forth. And that change, smaller than 1,000th of the width of a proton, is registered as a signal. The source of the 2015 detection was 2 black holes, each roughly 30 times the mass of the Sun, that had been spiraling together over billions of years and finally merged, producing a brief burst of gravitational radiation. The collision had happened over 1 billion light-years away. Its energy, released in an instant, exceeded that of all the stars in the observable universe shining together. Yet almost all of it was carried away as invisible gravitational waves, detectable here only as that barely measurable shiver in the fabric of space. LIGO heard it, a chirp, rising in frequency and amplitude for a fraction of a second, then silence. A moment encoded in data that confirmed one of Einstein's boldest predictions a century after he made it. Since then, dozens of gravitational wave events have been detected, merging black holes of various sizes and colliding neutron stars. One particularly significant event, in 2017, was the merger of 2 neutron stars. Unlike a black hole merger, this collision produced not only gravitational waves but also light, a burst of gamma rays, followed by an afterglow visible across the spectrum. Telescopes around the world turned toward the source and observed it simultaneously with the gravitational wave signal. That event confirmed something that had been suspected, but not directly proven. Heavy elements, including gold and platinum, are forged in the collision of neutron stars. The spectral signatures of gold and other heavy elements were directly detected in the light. From the aftermath of that merger, much of the gold on Earth, the gold in any ring, in any piece of jewelry, in any electronics, was almost certainly born in such cataclysms, scattered into space and eventually gathered into our solar system. Gravitational wave astronomy has opened what scientists describe as a new window on the universe. Before 2015, we observed the cosmos almost entirely through electromagnetic radiation, light of various wavelengths, from radio waves to gamma rays. Now we can observe it through the geometry of spacetime itself. There may be sources of gravitational waves, cosmic strings, phase transitions in the early universe, the echo of inflation itself that produced no light at all, and which only this new sense can detect. We are at the very beginning of this new era. The patience required for this kind of science is itself remarkable. LIGO was funded, designed, built, and operated for decades before its first detection. There were long stretches of null results, technical challenges, and no guarantee that the sensitivity required would ever be achieved. The scientists and engineers who built it were working on timescales, longer than many careers, toward a goal that was not certain. And then, in 2015, the universe spoke, and they were ready to hear it. That patience, that willingness to work across decades toward a distant and uncertain goal, is one of the quietly beautiful things about astronomy. It is a science conducted at the pace of a long life, or sometimes across multiple generations. Some projects take decades to come to fruition. Some questions being asked today will not be answered in our lifetimes. And somehow, that is all right. The questions are worth asking. The work is worth doing. The universe will still be there, with its answers. When the instruments are good enough and the time is right, breathe slowly. Let the images settle. Two neutron stars circling each other for billions of years, drawing closer, until in a final instant they merge and scatter gold into the galaxy. Somewhere in that gold is the matter that eventually became part of you. The universe has been working toward you in its slow and unhurried way for a very long time. Let us think now about some of the stranger and more speculative aspects of cosmology, not as definite truths, but as possibilities, as the honest edge of what we know, where physics gives way to imagination disciplined by mathematics. One such idea is the multiverse. The Big Bang, as we understand it, was not necessarily a unique event. In the theory of cosmic inflation, a very rapid expansion of the universe in the first tiny fractions of a second after the Big Bang, the physics of that expansion may not have ended cleanly. Some models of inflation suggest that different regions of space exit the inflationary phase at different times, and each such region becomes its own separate universe, expanding independently, possibly with different physical constants and different laws of nature. In this framework, our universe, with its particular values for the speed of light, the strength of gravity, the mass of electrons, and all the other constants that define physical reality, is one bubble in a vast, perhaps infinite, sea of bubbles. Other bubbles may have constants that make complex chemistry impossible, or stars that form and die too quickly for planets to develop, or no matter at all. Some may have constants almost identical to ours, so that versions of reality very similar to what we know exist in infinite number, differing only in the smallest details. This is called the multiverse, and it is a genuinely open question whether it is a scientific theory or a philosophical speculation. It makes predictions that are, in most versions, extremely difficult to test. We cannot look beyond our cosmic horizon to see other bubble universes. We can look for indirect evidence, patterns in the cosmic microwave background that might represent an ancient collision between our bubble and another. But so far, no such signature has been definitively found. Some physicists embrace the multiverse as a natural consequence of well-supported inflationary models. Others are skeptical, arguing that a theory that cannot be tested is not, strictly speaking, science. This tension is real and ongoing, and it is not resolved. You don't need to take a position tonight. You can simply hold it as a remarkable question. Is our universe all there is? Or is it one small region in something unimaginably larger? Another speculative but mathematically legitimate concept is the wormhole. Einstein's equations of general relativity allow for solutions in which two separate regions of spacetime are connected by a tunnel, a shortcut through the fabric of space. In principle, one could enter such a tunnel at one location and emerge at another location far away, or even at a different time. The mathematics permits this. The question is whether such structures could actually exist, and if so, whether they could be stable. Current physics suggests that a natural wormhole would collapse almost immediately unless held open by some form of exotic matter with negative energy density, a substance we have no direct evidence for, though quantum physics hints at its theoretical possibility. Some researchers have explored whether quantum entanglement, the strange connection between particles that have interacted in the past, such that measuring one affects the other no matter the distance, might be related to microscopic wormholes at the quantum scale. This is deeply speculative and unconfirmed, but the possibility, however remote, of bridges through space and time has a certain quality to it that invites wonder without demanding belief. It is the honest frontier of physics. Here is what the mathematics allows. Here is what we do not know. Here is the space where imagination and calculation meet. You can let those images drift through you gently. Tunnels in spacetime, regions of the early universe still glowing with ancient light. Neutron stars spinning hundreds of times each second, gold scattered by the deaths of stars, dark matter flowing through everything. None of these require you to understand them fully. They are just pieces of a very large, very old, very beautiful story, and you are resting inside it. Let your shoulders sink a little deeper. Let the weight of your body settle fully into the warmth of your bed. The details don't matter right now. The feeling is enough. Let us drift now to some of the places in our own solar system that astronomers have been looking at with new eyes in recent years. Worlds that have turned out to be far stranger and more interesting than anyone expected. And where the question of life beyond Earth has moved from science fiction closer to genuine scientific possibility. Consider Europa, a moon of Jupiter roughly the size of Earth's moon. On the surface, it is covered in ice, crossed by a network of long linear cracks and ridges that suggest the ice layer is moving, driven by tidal forces from Jupiter's immense gravity. Beneath that ice, perhaps 5 to 30 kilometers thick, depending on the region, is a vast ocean of liquid water. Estimates suggest this ocean may contain twice as much water as all of Earth's oceans combined. The ocean is kept liquid by tidal heating. Jupiter's gravity stretches and squeezes Europa as it orbits, generating friction within the moon's interior, producing heat. This is the same kind of heating that keeps the interior of Earth's moon geologically dead, but in Europa, it is strong enough to melt a global subsurface ocean. Water, warmth, and chemistry. The three ingredients that, on Earth, have been sufficient for life to arise and thrive. Scientists cannot yet say whether life exists in Europa's hidden ocean. But the question is no longer absurd. It is a genuine scientific question, and missions are being designed to investigate it. NASA's Europa Clipper spacecraft is on its way to the Jovian system, designed to fly repeatedly past Europa and study its ice shell, its ocean, and the plumes of water vapor that appear to erupt from cracks near the South Pole. If life exists in Europa's ocean, it would be entirely unlike anything we know on Earth's surface. It would exist in perpetual darkness, with no access to sunlight. It would derive its energy from the chemical reactions between the ocean and the rocky seafloor, or from hydrothermal vents, where heat from the interior drives chemistry. Some scientists believe this kind of life is not only possible but perhaps inevitable wherever the conditions are right. Others are more cautious, but the possibility that beneath the cracked, frozen surface of a moon, circling a gas giant, in an ocean no sunlight has ever touched, living things might exist, is genuinely one of the most remarkable things to sit with quietly in the dark. And Europa is not alone. Saturn's moon Enceladus, only about 500 kilometers wide, also has a subsurface ocean. It erupts continuously, spraying geysers of water vapor and ice particles from cracks near its south pole, and those plumes have been sampled directly by the Cassini spacecraft, which flew through them multiple times. The plumes contain salts, organic molecules, hydrogen gas, all signatures of chemical activity between liquid water and rock, the same kind of activity that drives hydrothermal vents on Earth's ocean floors, where rich communities of life thrive in complete darkness. Titan, Saturn's largest moon, presents a different and equally strange possibility. It has a thick nitrogen atmosphere, rivers, lakes, and seas on its surface. But those seas are not water. They are liquid methane and ethane, hydrocarbons that are gases here on Earth, liquefied by Titan's extreme cold. On Titan, a methane cycle operates analogously to Earth's water cycle. Methane evaporates, forms clouds, rains down, fills rivers, flows to the seas. The landscape, in some images from the Cassini-Huygens mission, is eerily reminiscent of Earth. River deltas, coastlines, dunes, except that everything is made of the wrong material, at temperatures far below freezing, under an orange haze of nitrogen and hydrocarbon clouds. Could life exist in Titan's methane seas? It would have to be chemically utterly unlike life on Earth. Water-based biochemistry would be impossible there. But some researchers have proposed theoretical chemical systems that could, in principle, function in liquid methane. This is deeply speculative, but the question is interesting enough that a NASA mission called Dragonfly, a rotorcraft designed to fly through Titan's thick atmosphere and land repeatedly at different surface sites, is in development and planned for arrival in the 2030s. The solar system, it turns out, is not a collection of dead rocks orbiting a star. It is a collection of worlds, each with its own history, its own strange character, its own quietly interesting secrets. Some of those secrets we are only now beginning to read. And beyond our solar system, around other stars, in the years since the Kepler Space Telescope was launched in 2009, we have discovered thousands of planets. We now know that planets are not rare. They are abundant, orbiting stars of all types, in all sorts of configurations, at all sorts of distances. Some are hot rocky worlds tidally locked to their stars, always showing one face to the light and one to the dark. Some are gas giants with no solid surface. Some are what astronomers call super-Earths, worlds larger than ours but smaller than Neptune, possibly rocky, possibly with thick atmospheres, possibly with liquid water. We have found planets in the habitable zones of their stars, the regions where temperatures could allow liquid water on the surface, depending on the atmosphere. We have detected the chemical fingerprints of atmospheres on some of these distant worlds, using the technique of transmission spectroscopy, where starlight passing through the planet's atmosphere, as it crosses in front of the star, carries the absorption signatures of the gases present. We have not yet found oxygen or water vapor in the atmosphere of an Earth-like planet. But the instruments are getting better. The next generation of telescopes may be capable of detecting biosignatures, chemical signs of life, in the atmospheres of planets dozens of light years away. Whether we find anything or find nothing, both outcomes would tell us something profound. Finding life would mean the universe is alive in ways we can barely imagine. Finding nothing, planet after planet after planet, would mean life here is so rare as to be nearly unique, which would raise its own quiet questions. For now, the search continues, patient yourself rest inside that search for a moment. Let the images drift. Ice-covered moons with hidden oceans, methane rivers on orange worlds, the light of distant stars carrying the chemical signatures of their atmospheres. Let them pass through your mind gently, like clouds. You don't need to hold any of it. Just let it float. We are drawing close now to the quieter reaches of this journey. The pace of words is slowing. The universe, which we have been crossing together all this time, will soon give way to something simpler, to the darkness above you, the stillness of the room, the soft rhythm of your own breathing. But let us stay a little while longer in the deep. There are a few more things worth touching, gently, before we let go. We have spoken of stars being born and dying, of galaxies colliding and merging over billions of years, of dark matter and dark energy shaping the universe from the outside, of black holes where time bends, of oceans beneath frozen moons. But there is a deeper philosophical question that all of this astronomy eventually leads toward. A question that does not have a scientific answer yet, and may not have one for a very long time, if ever. Why is the universe the way it is? Not in the sense of which physical laws apply. We have made great progress in understanding those. But in the sense of why those laws have the values they do. Why does gravity have the strength it has? Why do electrons have the mass they have? Why is the speed of light exactly 300,000 kilometers per second, and not twice that or half? These constants, the fundamental numbers that define the behavior of everything in the universe, were not chosen by any calculation. They simply are what they are, and they are extraordinarily finely tuned for the existence of complex structures. If the strength of gravity were slightly different, stars could not form the way they do, or they would collapse too quickly for planets to develop. If the ratio of the electromagnetic force to gravity were slightly different, the chemistry of life would be impossible. If the cosmological constant, the energy of empty space, were even slightly larger, the universe would have expanded so quickly after the Big Bang that matter never had time to clump together into galaxies and stars and planets at all. This observation, that the constants of nature seem finely adjusted for the existence of complexity in life, has no agreed scientific explanation. It is simply a feature of the universe that we observe and find remarkable. Some scientists and philosophers find this remarkable in a spiritual way, though we can set that aside without dismissing it. Others find it unremarkable, arguing that we could only find ourselves in a universe compatible with our existence. So of course we observe one, the argument from selection. If you wake up alive, it is because the universe allowed you to survive the night, not because the night was especially designed to keep you safe. Others take the multiverse seriously partly because it would explain the fine-tuning. If there are an enormous number of universes, each with different physical constants, then it is no surprise that we find ourselves in one where life is possible. Only in such a universe could there be anyone to find themselves anywhere. None of these answers is complete. None is definitive. This is an open question, held at the intersection of physics, philosophy, and the honest acknowledgement of what we do not know. And that is fine. Some of the most important questions do not have clean answers. They sit with us, unresolved, enriching our sense of the mystery and depth of things. A universe that raised more questions than it answered would be a universe still worth living in. A universe still full of things to wonder about? You don't need to answer any of these questions tonight. You don't need to answer them at all. Just let them be there, the way the stars are there. Whether you can see them or not, whether you are thinking about them or not. Let your mind go a little softer now. The experiments that astronomers and physicists are designing and building and running right now, around the world and in orbit around the Earth, and far out into the solar system, are extraordinary in their patience and precision. Let us visit them briefly, gently, before we close. Far above the Earth, the James Webb Space Telescope drifts at the second Lagrange point, about 1.5 million kilometers from Earth, in the direction away from the Sun. It is kept in permanent shade so that its infrared detectors can look at the universe without interference from the Sun's warmth. Since it began observations, it has captured images and spectra of galaxies so distant that their light left them when the universe was only a few 100 million years old. It has found galaxies that seem to have formed earlier than our models predicted. Galaxies so massive and so structured in the universe's early time that scientists are still working to understand how they grew so quickly. It has looked at clouds of gas around newly forming stars, revealing the chemistry of the disks from which planets are being made. It has measured the atmospheres of exoplanets with unprecedented detail. And it continues to look, night after night, gathering photons that have been traveling through the cosmos for billions of years, just waiting for an instrument sensitive enough to catch them. On the ground, the next generation of extremely large optical telescopes are under construction in Chile and in Hawaii. These instruments, with primary mirrors 30 or 40 meters across, will be powerful enough to study the atmospheres of Earth-sized planets around nearby stars. They may, within the next decade or two, be capable of detecting oxygen, water vapor, and methane in the atmospheres of worlds tens of light years away. If those signatures appear together in the right proportions, they would constitute powerful, though not conclusive, evidence of life. Underground, in mines and tunnels in multiple countries, dark matter detectors grow more sensitive with every generation. Some are filled with liquid xenon, kept at extremely low temperatures, watching for the tiny flash of light that would indicate a dark matter particle scattering off a xenon nucleus. Others use germanium crystals cooled to temperatures just above absolute zero, where even a tiny energy deposition can be detected as a vibration. Every year, the detectors become more sensitive. Every year, the search becomes more thorough, and though dark matter has not yet been directly detected, each experiment eliminates more possibilities, narrows the range of what dark matter could be, and brings us, quietly, closer to an answer. In space, the Euclid mission, launched in 2023, is mapping the three-dimensional distribution of billions of galaxies across 10 billion light-years of cosmic history. By measuring how the pattern of galaxy clustering has changed over time, it will produce the most precise measurement yet of how dark energy has affected the universe's expansion. Is dark energy constant, as a cosmological constant would predict, or does it vary with time? Euclid is designed to answer this question, or at least to narrow the possibilities substantially, and gravitational wave observatories continue to listen. The LIGO and Virgo detectors have been upgraded repeatedly, and will be upgraded further. Plans are underway for a space-based gravitational wave observatory, called LISA, the Laser Interferometer Space Antenna, which which would consist of 3 spacecraft separated by millions of kilometers, forming an enormous triangle in space, sensitive to gravitational waves far lower in frequency than ground-based detectors can reach. LISA could detect the gravitational waves produced by the mergers of supermassive black holes in distant galaxies, or the background hiss of gravitational radiation from the early universe itself. It is planned for launch in the mid-2030s. All of this, the telescopes, the underground detectors, the space missions, the mathematical models and simulations running on the world's largest computers, represents an ongoing, collective, patient effort to understand the universe. It is conducted by thousands of people across dozens of countries, across generations of instruments and ideas. Much of the work is slow. Much of it produces null results, or results that complicate rather than simplify the picture. And yet it continues, because the questions are worth asking, and because the universe, for all its mystery, has proven willing to answer, if only you ask carefully enough, with instruments precise enough, and patience long enough. There is something deeply reassuring about that. The universe is not hiding. It is just very large and very subtle, and requires very careful looking. But it does yield its secrets, one by one, to those willing to wait. You can let that be a comfort as you drift towards sleep. The universe is not unknowable. It is simply not yet fully known. And the work of knowing it continues tonight, while you rest. Let your breathing deepen a little. Let your thoughts become less sharp. We are almost at the end of our journey, and the end is the quietest part. Everything we have discussed tonight, the scale of the cosmos, the life and death of stars, the invisible structures of dark matter, the accelerating expansion driven by dark energy, the strange behavior of time near massive objects, the hidden oceans of distant moons, the gravitational waves that carry the news of collisions across 1 billion light years, all of it circles back, eventually, to a single quiet fact. You are here, not in spite of all of this, because of it. The atoms in your body were forged in the cores of stars that lived and died billions of years ago. The water in your cells may have arrived on Earth aboard ancient comets, carrying it from the cold outer reaches of the early solar system. The carbon chains that make up your DNA are built from elements scattered by supernova. The iron in your blood was made in the final moments of a dying star, in the last seconds of nuclear fusion before collapse. You are not separate from the cosmos. You are a part of it, a temporary, local arrangement of matter and energy that the universe has organized over billions of years of chemistry and gravity and chance into something capable of thought and feeling and wonder. When you look at the stars, or simply lie here in the dark, knowing they are there, you are the universe looking at itself. Through your curiosity, through your awareness, the cosmos has, in some small place, become conscious of its own existence. That is not a small thing. It may be one of the rarest and most remarkable things in the known universe. And yet you also need to sleep. The universe does not require your attention tonight. It will continue without it. Stars burning, galaxies drifting, dark matter flowing through everything in its invisible way, the background microwave glow of the Big Bang persisting in every direction, ancient and undimmed. All of that will continue whether you are awake or asleep, whether you are watching or resting. The cosmos cosmos is patient. It has been here for 14 billion years. It will be here when you wake. So you can let go now, not of anything important, just of the need to hold on. Let the facts soften into feeling. Let the numbers dissolve into the simple sensation of being very small inside something very large. Let the questions blur and become quiet, like lights going out in a distant city seen from above, one by one, until there is only the dark and the stars and the slow turn of everything. Your body is heavy. Your breathing is slow. The thoughts that were moving through your mind have grown gentler, less insistent, more like weather passing than like problems to solve. That is exactly where you want to be. The night sky above you, even now, even through walls and clouds, and whatever lies between you and it, is full of the things we have been talking about. Faint light arriving from billions of years away. Dark matter flowing past in invisible rivers. The cosmic microwave background filling every corner of space with its ancient warmth, just barely above absolute zero. Somewhere out there, neutron stars are spinning. Black holes are quietly curving spacetime. Somewhere, two galaxies are beginning the long, slow, beautiful process of collision and merger. Somewhere, a protoplanetary disk is spinning around a young star, and rocks are beginning to accumulate under gravity, and the long, patient process of world-making is beginning again, as it has begun countless times before, as it will begin countless times again. And here, you are breathing. Here, you are warm. Here, everything you need for tonight is already present. The day is behind you, and the night is holding you. And the universe, vast and old and full of things no one yet fully understands, is simply here, the way it always is, indifferent to the hour, and yet somehow containing everything. You don't need to understand it. You don't need to remember any of what we have spoken about tonight. The details can go. The names, the numbers, the theories, the mysteries. You can let all of it release, like breath. What remains, if anything, can be something quieter. Just the sense of scale. Just the sense of wonder. Just the feeling of being inside something very old, and very large, and very much still unfolding. That feeling is enough. It has always been enough. If these quiet journeys help you rest, you are always welcome to return to deep somna whenever you need to drift away again. For now, there is nothing more, just the dark, just your breathing, just the stars above, steady and ancient and unconcerned, burning their slow fires across the night. Sleep